All right, so we got about a minute to go, and what I'm doing is to continue with the discussion on Monday because I said I would give you guys another proof by induction thing, so I'm doing that right now. So first of all, I defined a function f, okay, f of n. So I'm gonna use an implication here. So when n equals to 0, then we define f of n. Well, okay, there are several ways to define this. I'm going to use the other way to do it too. So we'll define f of n as depending on whether n is 0 or not. So if n is 0, okay, so n is a natural number. I would start from the beginning, when we get into the class time, which is in about 30 seconds. So don't worry if you're just coming in and have no idea what I'm talking about. Okay. All right, so it is time. It is noon time. So I'm gonna get started here. From the Discord channel, we have about maybe half of the class here. But it's okay. It's getting recorded on the other side, being streamed to YouTube as we speak. So I'm gonna get started here. All right, so this is what we're doing. We are limiting the scope or the domain of function f. So n is going to be a natural number in all the further discussions. And I'm going to define function f, this is f of n, to be a ternary expression. And I know how some of you really like the use of ternary expression. No, I'm just kidding. I personally like the use of ternary expression, but I know most people, look at it and go like, no, not ternary expression again. But I really like it. Okay, so in a ternary expression, the first sub-expression is a condition, is either true or false. If the first sub-expression is true, then this becomes the return value of the entire expression. If the first sub-expression is false, then this becomes the value of the entire expression. So that's basically how a ternary expression works, and I'm assuming all of you kind of know this already, but I just want to use this as a reminder. Alright, so when you look at this f of n, as a recursive function, it doesn't look like n squared at all, okay? So, but I claim that f of n is n times n, and I want to use proof by induction to show that is the case. Alright, so this is a how should I put it? It is an example, okay, of how to use proof by induction as a concept. All right, so let's go ahead and do this. The base case, okay, the base case of proof by induction is basically to say, what happens when n does equal to 0. Okay, so on one side, we want to evaluate f of 0. And what do you think f of 0 should become? What is the value of f of 0 given that we define f of n up here? I'll give you guys some time to think about it and let me know, what the answer is supposed to be. Absolutely. So Jack, your mic is on.
Oh, my bad.
No problem. All right. So yes. So this is actually 0, okay? Because when n does equal to 0, we just return a 0. Okay. What about the other side? What about n squared? Okay, so 0 squared, 0 times 0 is also 0. So now we have just established that f of 0 is indeed not just the value of 0, but it is 0 squared. Okay, which is basically saying, oh, okay, so the theorem turns out to be true at least when n equals to 0. So that's the base case. So typically the base case is really easy to prove because you are just substituting a variable, that we use in the theorem with a very specific value, and then you just have to evaluate, in this case, the left hand side, and then evaluate the right hand side and show that, hey, these two are the same. So now we're done with the base case. So the induction step is a little bit tricky. Okay, it's tricky not because of algebra, but because of the concept. Because the induction step has two subparts. The first part of the induction step is the induction assumption. So the assumption is for some n equals to k, okay, for some k, okay, when n equals k, the theorem is true. Okay, so what that really is saying is for some k, f of k is indeed k's times k. All right, so that's an assumption. So don't ask me which specific value is k, because that's the whole point, is we don't need to know. Okay, all we need to know is there exists at least one k, which is a natural number, such that f of k equals to k times k. All right, so the next step in the induction step, okay, here, oops, over here. So the second step is to use the assumption to prove that when n equals to k plus 1, the theorem is true as well. Okay, so this is the proof. So now we need to prove that f of k plus 1 is also k plus 1 times k plus 1. Okay, so how do we do that? The first thing we do is we apply the definition of f. So we basically plug in k plus 1 all the way up here, and then we ask, okay, we are dealing with k plus 1, and k itself is a natural number. Since k itself is a natural number, which means k has to be at least 0, so 0 plus 1 is not going to be 0. So we are not going to use the true value here. We're going to use the false value over here. So by the definition of f, okay, by the recursive definition of f, now we conclude that that is going to be f of k plus 2 times k plus 1, and then minus 1. And okay, so this is eventually what we want to prove. Okay, so I'm going to move this aside. So the first thing we do is we look at f of k plus 1, and then we turn that into f of k plus 2 times k plus 1 minus 1. So are we good with this step? Does everybody understand how I just applied the definition of f of n so that I can say, okay, well, since k is at least 0, we know that we cannot use the constant 0 over here, and we have to use the recursive definition over here. Are we good with this step? Because if we're not good with this step, then it doesn't make sense to move on. Okay, all right, so we got at least one confirmation. Very good, thank you. Now we move on, and we look at this and go like, okay, what are we going to do about this f of k? Well, the answer is nothing, because we have the assumption, right? Because we have the induction assumption that f of k is k times k already. So now we say this is the same as k times k plus 2 times k plus 1 minus 1. And now we apply algebra, right? So algebra says k plus k has to be out here, and then we use distribution. So we have 2k, because we distribute the 2 multiplied to k plus 1 as a whole. And now, because we have 2 times 1 and then the whole thing minus 1, so we have basically just 2 minus 1, which is of 1. And I'm pretty sure all of you recognize that this is really just k plus 1 squared. Okay, this is k plus 1 squared, but it's difficult for me to write squared, so I'm just going to use this is k plus 1 times k plus 1. Done, right? So we are now done with this proof, because we have just taken the original form of f of k plus 1 all the way to the form that we want to see, which is k plus 1 times k plus 1. So now we have just proven, we are done with the induction step. So combined with the base case, now we have proven the original theorem. That is proved by induction. So I'm gonna let you guys look at this and think about it for a little bit. And if you have questions, go ahead and ask questions, because this is a fairly abstract concept. I would say compared to proof by contradiction, proof by induction is, I would say, it's weird in its own way. Okay, it's not any harder or easier, but it is just weird in its own way. All right. Any questions? All right, Aiden is going to ask something. All right, so Aiden's asking about the omega homework. Are we supposed to get ABBA, or BAAB is also fine? It can be either way. So the ordering within the permutations, between the permutations. In other words, the inter permutation part is not important, but the intra permutation part is important because permutations are order specific. Okay, cool. All right. Any questions related to proof by induction? Because this is our second exposure to proof by induction. Okay, well, while you guys are thinking about whether you have questions about proof by induction, let me just explain why it is important. Okay, proof by induction is important because of recursion. Because recursion works kind of the same way. You need a condition to stop the recursion, right? That basically becomes your base case. And in order to prove that a subroutine or an algorithm that is recursive by itself is correct, we can now apply proof by induction. So that's why proof by induction and recursive algorithms, they kind of go hand in hand, because one is a technique to prove the correctness of an algorithm, and then the other one is how we express the algorithm, and they match up really, really well. All right, so Anita is asking, so is it always the case when proving by induction that we first check n equals to 0 and then k plus 1? It depends on the domain, okay? Because it depends on the domain of n. If the domain of n has a natural end, like in this case, we have natural numbers, and with natural numbers, 0 is a very good starting point because there's nothing smaller than 0 in the set of natural numbers. So in that case, yes, it does make sense. On the other hand, if you're dealing with, let's say, if the domain are all the integers, including the positive and the negative, then you don't have a natural end to begin with. So in that case, you basically start with n equals to 0, and then you have two subparts when it comes to the induction step, because one subpart says, assuming the theorem is true for k, you have to prove it is also true for k, the case of k plus 1, and then the other one says, if you assume that it is true for k, then you also have to prove that it is true for the case of k minus 1. So that's kind of the tricky part. Okay, so Aiden types, if you prove, k plus, okay, if we can prove the case of k plus 1, assuming it is true for the case of k, shouldn't it also work backwards? That is a very good question. It depends on, in the chain of reasoning, whether we have true equality or whether we rely on just implication. if we only rely on implication, which only goes in one direction, then we cannot reverse the direction and go like, well, since we can prove the case for k plus 1, we can reverse everything and prove the case for k itself. I suppose so. Okay, if the entire chain of reasoning, so I'm just answering Damon's, not Aiden's, sorry, Aiden's question. If you can, if the whole process is based on algebra, then it's okay. Yes, you can, because algebra goes in both directions. Because you can go in one direction like this, you can also reverse the direction going back to the original one. But if the chain of reasoning is not entirely based on algebra and there's implication used in the derivation, then it is not reversible. Because when you use algebra, it is fully reversible because it is not a implication, it is a if and only if. So that's why it depends on the actual steps of the proof. In this case, it does work backwards too. But in some cases, hypothetically, if the chain of reasoning is not only using equality, then it may not be reversible. Okay, alrighty. Alright, so that's proof by induction, which looks like a little side dish. Okay, since the main topic here is about probability, discrete probability, but proof by induction is a very important topic by itself. Okay, because a lot of proofs in algorithms, like the correctness of algorithms, those are also done by proof by induction. And I'm just going to address one additional thing that some of you may be thinking, and some of you may be thinking, but not all algorithms are recursive. So what about those that are not recursive? What if we have an algorithm that is based on loops? Then proof by induction doesn't work anymore. The interesting thing is the expressive power of recursion versus iterations, they are actually equivalent. In other words, if there's a way for you to use a loop, like a while loop or for loop or do while loop, to express an algorithm, there is a way to express the same algorithm using recursion but without using loops. Okay? And it is true the other way around as well. Okay, so if you take any well-known recursive algorithm, okay, we'll take the construction of a binary search tree. Okay, that is typically recursive because it's easier to express it in a recursive way. But you know what? You can also do it without using recursion. You can use it. You can basically use just loops and an array, to implement your own stack to express the same algorithm. So they are basically they are equivalent when it comes to what type of logic they can express. One is recursive, the other one is not. But the recursive one lends itself to proof by induction because the structure of proof by induction and the structure of a recursive algorithm, they match up very, very well. So that's why proof by induction is really kind of cool because you can use it as a technique to prove the correctness of many algorithms, including the ones that you think is like, well, this one should not apply because it's an iterative algorithm. It's not recursive because you can turn it. You can turn it either way. And it is easier to take something that is iterative and turn it into recursive than the other way around. Turning something that is by nature recursive into something that is iterative is doable, but it just takes some extra work. Yep, it's kind of cool. All right, so now that we are done with proof by induction, what we'll do is now we continue to talk about binomial distribution. So the binomial distribution in this case is basically saying if I have n coin flips, okay, so in this particular expression here, if we have n coin flips and p is representing the chances of landing on the head, q is representing the chances of landing on the tail, And in this case, m is the number of times the coin lands on the head out of n times. This expression here is telling you the probability of, just the coin landing on the head m times over n total number of coin tosses. Okay, so it's really neat, right? I mean, look at just this equation. Look at how neat the equation, the expression is. So over here, in the last section here, it's basically talking about, based on observed probabilities. In other words, somebody is actually watching someone, flipping a coin and just counting, out of 5 flips, how many times we get, the 3 heads, how many times we get 2 heads, 1 head, 0, 4, and 5, and so on. So based on those observations, can we go back and try to figure out, whether the coin is loaded or not? So that's kind of what this paragraph is about. All right. So I want you to think about actual useful practical applications of binomial distribution. In other words, you kind of have to think about in real world, what type of distribution is binary. Okay, either one way or the other, and there's a probability involved, and it is important for us to understand what are the chances that one particular possibility happens, or once, twice, 3 times, and so on. And it's going to be limited to the scope of computer science, right? So I'll give you a hint. Let's just say that we are talking about a Wi-Fi network, and depending on what frequency you're using, if you're using one of the older Wi-Fi routers, which uses 2.4 gigahertz as the main carrier frequency, that turns out to be the same frequency that most microwave oven uses, because that's also the frequency where I cannot remember which one, but one of the vibration of the water molecules is resonates at about 2.4 gigahertz. Yeah. I cannot remember which one, because the water molecule is kind of like this, right? Because you have the oxygen and then the 2 hydrogen like this. So it vibrates in multiple ways. It can vibrate this way, but it can also vibrate this way. But I cannot remember which one, but it resonates at about 2.4 gigahertz. And that's why a microwave oven, the microwave itself, okay, is at about 2.4 gigahertz. So that's why, when you use a microwave oven, near a Wi-Fi router, some people may have may lose their connection, because they one can interfere with the other one, and a microwave has a lot more power compared to a Wi-Fi router. Okay, so think about that scenario. So now we want to calculate the chances that a single bit is mistransmitted. Now, I know this is simplifying things a whole lot, okay, but we'll just kind of use this very simplistic model here. So let me go back to the editor here. So we're going to say P is the chances that a bit is transmitted correctly. So it should be pretty close to 1, so I'm going to say this is 0.9999. Okay, so Q is always just 1 minus P, which is the chances of a bit transmitted incorrectly. Okay, so given this, okay, and given a packet, okay, which is a single unit, where if it is an error, it is usually detectable, and then we have to retransmit the entire packet. So we'll just make an assumption here and say assume a packet has 1024 bits. Okay, and that's including the checksum and everything. Okay, so I want to calculate, okay, what are the chances that a packet is transmitted incorrectly and requires a retransmission. Okay, so I think that's a fairly fair thing to do and to calculate in the context of computer networking, right? So what you do is now you look at this equation here and you say, okay, so we can do the calculation of if because anything other than all 1024 bits transmitted correctly, they are all the rest. They're all having at least one error bit, right? So what we want to do is to say the chances of not having any error bits is what? Well, let's think about this, right? So we're using combin, which is the choose notation here. So now we have 1024 bits, and none of them is supposed to, oh, I should say, all 1024 are transmitted correctly. So we have 1024 choose 1024 because we want every single one to transmit correctly. So now we have P to the power of 1024 times Q to the power of 0 because we don't want to have any single error bit. So when you substitute, okay, and P equals to 0.9999 and Q equals to 0.0001. So when you substitute these two values into this equation here, obviously Q is not really important because Q is only raised to the power of 0. But if you plug in these numbers, that would be the chances that a packet is transmitted without any error. So when you subtract that probability from 1, that would be the chances of having at least one bit of error in the transmission. So what does that do for you, right? Well, it can give you an estimate, okay, of throughput of the system, because occasionally we have error bits in the packet and then we have to retransmit. So it will give you the ability to basically calculate the theoretical throughput, because of the chances of basically transmitting a bit incorrectly. So when you change this number to, let's just say 0.9, which is really, really bad, you can see how that is going to impact the chances of transmitting a packet correctly. So that's one kind of practical application of discrete probability. All right, so do we have any questions? Do we have any questions about counting, which has to do with combination and permutation, or discrete probability, which is what we are doing right now? And binomial distribution is the only one that we are concerned about in discrete probability distribution. I don't see any questions. All right, so if there are no questions, then we are going to move on to the next topic. All right, so let's go back to take a look at all the modules. We still got a few to go. All right, so if we scroll down, there's graph, there's predicate calculus, and I think there's also the notations of big O, little o, big omega, little omega, big theta, and little theta. All right, so of the three main topics here, okay, these are the remaining three topics that we need to go through for the rest of the semester. I am going to say that the predicate calculus, as fun as it is probably the least important for most people. The big O notation is probably the most important, and then graphs are kind of like in between. So I kind of like the way things are ordered in this case. We'll go over the big O, big omega, and big theta notation first, and then we'll get to graphs. And if we still have time before the end of the semester, then we'll get to predicate calculus. Predicate calculus is kind of like a souped up version of propositional logic, but better, right? Because I did say souped up, right? So the souped up portion has to do with in propositional logic, there's no way to have a parameter. Okay, when we deal with the PK RST, those are all individual pieces of facts. Okay, they're not predicates. They don't take a parameter and say whether something is true or false, given the parameter itself. Okay, so that is kind of limiting in terms of the kind of reasoning that we can perform, because it makes it impossible to use a quantified statement in the case of propositional logic. So predicate logic or predicate calculus does allow the specification of quantifiers, so we can do a whole bunch of a different type of a different type of reasoning using predicate calculus that we could not have done using propositional logic. So it's interesting from that perspective. And there's also a programming language called Prolog that can basically do all the reasoning for us, and it's kind of fun to program in Prolog and see how it can figure out things on its own, okay, quote unquote on its own. So that's kind of fun, but for the most part, most of us don't have to deal with predicate calculus, but all of us will have to understand the big O notation, so that we're going to start with the big O notation over here. All right, so this is our new topic, and I haven't had a chance to regenerate yet. So the notation stuff, may not be when you right click on it. It doesn't give you the LaTeX. Oh, it does. Oh, okay, nice. Okay, so I changed the way I compile my LaTeX document into HTML. So probably last semester, because it's working now. Okay, very good. So what we're going to do is we will first look at an algorithm like this one here. So we'll take a quick look at the algorithm, and then we'll say, okay, but how do we know how much time it takes to finish this entire algorithm? Lines 1, 2, and 3, they typically do not, they're not really contributing much to the amount of time it takes, because all they do is to allocate storage, okay, for the local variables, so they don't really use up too much time. Lines 4, 5, well, I mean, they take up a little bit of time, but it's only done once, right? So it's not a big deal. So the majority of the time is taken by line 6, line 8, and also line 9. Line 6 does take up time because it is a comparison between I and n. So every single time we compare, it is a subtraction operation. For those of you who have taken CISP440 already, then you know that your comparison involves a subtraction, which takes time because you have to get through the ALU, the arithmetic and logic unit in the processor, to compute the subtraction, the difference between two numbers. But in this case, we need to look at the flags. But nonetheless, it takes time. And then line 8 and line 9 obviously will also take time because they have an addition to perform on each line, and also an assignment operation, which means we have to update a certain location in RAM, which also takes up time. So when you combine the entire thing, then the equation looks like f of n. If f of n is representing the exact amount of time for this algorithm to take when n is a certain number, then we have t1 plus t2 plus n, which is this n here, the parameter, times t2 plus t3. So if you want to know what all of these different t's are referring to, they are described in the previous two paragraphs. So in paragraph 1 here, okay, the first paragraph, T1 is referring to line 4 and line 5. The initialization of I and sum is going to take T1 amount of time. T2, on the other hand, refers to how much time it takes for one single comparison of I versus n. That is T2. And then T3 is referring to the total amount of time that will take up by line 8 and line 9. So the reason why you see T2 appearing twice is because it takes one extra iteration, or it takes one extra comparison to exit the loop. Because the last time you evaluate I is less than n needs to evaluate to false in order for the loop to exit. So when you compare the number of times that lines 8 and 9 would execute versus the number of times I is less than n is evaluated, the number of times of I is less than n is evaluated is going to be one more than the number of times that line 8 and line 9 needs to execute, which is just the number of elements in the array. So this is an exact number, okay? Which means if you can empirically measure T1, T2, and also T3, f of n will give you the exact amount of time that it's going to take in order for this algorithm to finish, given that you know how large the array is, which is uppercase N. All right. So are there any questions about how this f of n is the actual amount of time that it's going to take to complete this particular algorithm? All right, no questions. If there are no questions, we're going to move on. So there are more complicated algorithms. So we got bubble sort. We have so bubble sort and I think selection sort. They all have about the same time complexity. So T1 is representing something that only needs to be done exactly once. And then T2 is going to be something that we need to do exactly the number of times that there are elements in the array. And then we have T3, being the time constant for things that we have to perform. In terms of number of times, it is n squared. Now, some of you may say, but certain things we only have to do like n minus 1 times. Other things we only need to do n minus 1 squared times. That is true, but everything can be absorbed by the way we compute the constants T1, T2, and T3. So eventually, okay, we can boil down to just 3 coefficients, T1, T2, and T3, to describe the actual amount of time that it's going to take to complete a particular implementation of bubble sort. Okay. But this is kind of tedious, okay? To have to figure out exactly what T1 is, exactly what T2 is, and exactly what T3 is extremely tedious, because now you have to, because different architectures would have different constants, and then depending on the optimization of the compiler, it would also give you a different time constant. And the worst part is it also depends on whether you can keep everything in cache or not, because modern processor architecture has 3 levels of caches, right? And we have level 1, level 2, and level 3 cache, and depending on how much cache you have and depending on what else the processor needs to do, because there are other threads and other processes at the same time, that can change the time constant a whole lot. And guess what? None of that really matters, right? Because all we really want to know is the reason why we want to compute this kind of f of n most of the time, not all the time, but most of the time, is because we just want to compare 2 different algorithms. We are not really exactly wanting to know, okay, tell me the number of microseconds it's going to take for this algorithm to complete. That's not what we're trying to look for. We're just basically going like, okay, here's merge sort and here's bubble sort. Which one is better? That's usually the question. So that means, having to figure out the exact amount of T1, T2, and T3 is not really necessary. Alright, so and Aiden typed something here. It also varies from different times you run it. Yes, absolutely. Okay, so from the perspective of comparing different algorithms, the coefficients T1, T1, T2, and T3 really do not matter all that much. Because, if you think about it, okay, when n becomes really large, T1 usually just kind of disappears really fast. It becomes insignificant, okay, really fast. Even T2, would stop being significant after a while because n squared is going to grow a whole lot faster, okay. So the rest of this section basically just use an example to illustrate, why the exact amount of T3, is not even important. Okay, when I teach CISP440, when I taught CISP440, I have not taught that class for a long time. So when I taught that class, I always tell people, if you have a really old computer, even one of the mainframe computers, okay, that has tape drives, okay, and you have to sort the records stored on tape, and you cannot even load all the records into RAM first before you sort it because the amount of RAM on these earlier mainframe computers is very limited. But if you use merge sort, okay, and somebody else decides, okay, I have the latest and greatest, 16 core, 4 gigahertz processor with 32 gigs of RAM, I can load everything into RAM first and then sort everything in RAM. I don't need a smart algorithm. I'm just going to use bubble sort. Eventually, okay, when n is large enough, merge sort implemented on the mainframe computer using reels of tape is going to win. Okay, that's just reality. So we are not concerned about the actual coefficients. We are more concerned about the shape of the curve. Okay, because when you look at the plot of n squared versus the plot of n times log of n, now it doesn't even matter which log base you're using, because the log base is just changing a constant, which can easily be absorbed by T3. So n log n versus n squared, n log n grows a whole lot slower when n is large. So, okay, so somebody typed here, BOGO sort. I'm not sure about BOGO sort. And Angel mentions Apple M1 chip. I have no idea what the M1 chip is. Now I'm curious. Alright, so the M1 chip, atomic scale, packing the largest number of transistors we have ever put into. Okay. Okay, so it's a system on a chip, SoC. It's a 5 nanometer process, and I think AMD, some of the AMD processors were using 7 nanometer. So 5 does beat 7, not by much, but it does beat it. Okay. Alright, so it does have the smaller the transistor, the less time it takes for the transitions. So you're gaining in terms of processing speed, but it's still going to lose to merge sort. Okay, if you implement bubble sort on the M1 chip, the latest and greatest, and you implement merge sort on a 1960 IBM mainframe computer that requires reels of tape, actual moving parts, the mainframe will still beat the M1 chip if the algorithm is better. Alright, okay, so there's a bunch of stuff going on in the text channel. Oh, okay, BOGO sort is a joke. Well, BOGO sort can work efficiently if you have when you have unrestricted parallelism. So this way, you basically just have each branch to perform a random ordering of the thing, and you just need to make sure you just have to have a linear time algorithm to check whether it is sorted or not. So that can be super duper fast, yes, but that's assuming that you can start as many threads as you need for that algorithm to complete. Yep, exactly. Okay. Neural engine, and immediately thought of putting a brain in there on the M1 diagram. Okay. Yeah, neural engines are interesting too. I think most people think that neural nets can do more than what they actually can, but all right. So now we're going to get into the kind of the notations here, because the notation is usually what makes things really kind of difficult to read until we get used to the notation. So we are going to be doing asymptotic estimates. All right, so there are several terms that we're going to have to define here, okay, and this is the fun part of teaching this class, is basically just introducing a whole bunch of notations, and then we go back and go like, really? Do we really need to know these notations? Well, let's go ahead and start with this one. Okay, we'll start with supremum. So supremum has a few assumptions. So we're going to look at A as a partial order, or we'll look at A as a set where it is partially ordered by a particular less than or equal to relation. Okay. Now this is really abstract. Okay. I want to remind you guys that at this point we are not saying what A is. Okay. A can be the set of natural numbers, it can be the set of integers, and so on and so forth. But I didn't say anything like that, right? I just say that A is a set where it is partially ordered by a less than or equal to relation. This so-called less than or equal to relation may not be less than or equal to the way you understand with integers and whatnot. It is just a symbol. Okay, it is just a symbol that represents a relation, which is no more than a subset of the Cartesian product of A with itself. Okay, and the only thing we need is for the less than or equal to relation to be partially ordering with respect to A. So that's all we need to know. So that means, okay, in case you don't remember what is partially ordered means as a relation, the less than or equal to relation has to be reflexive, it has to be antisymmetric, and it has to be transitive. And that's it. Okay, this is all that we need to assume about the set of A. Okay. So now we look at a X, which is a subset of A, okay? And we're going to define the predicate. So this is the definition of a predicate. P is just the name of the predicate itself. Y is a specific value. And X is the subset that we are talking about here. And because P is a predicate, that means it returns either true or false. So now this expression is going to tell us when it is going to return true. So P returns true if and only if for all x lowercase x in uppercase X, in other words for every single element in X, X is less than or equal to Y. Alright, so that's P of Yx. Do we have any questions about what this P of Yx is talking about? The next sentence actually summarizes it in English. So the next sentence says the predicate P Yx means Y is an upper bound of X. Oh, why didn't you just say that? Well, because I like to use quantified statements. Okay, and if I just say that Y is the upper bound of X, well, I mean there can be different interpretations, right? Because the word upper bound can be understood slightly differently by different people. Some people may ask, okay, is the upper bound a part of X or not? Okay, some people may ask, is the upper bound tight or not? Okay, is the upper bound a tight upper bound, or are we just talking about any upper bound? So that means it is ambiguous. Okay, if I really just use those words, okay, in English or in any natural language, if I just use these words and you can translate that into any natural language, it's going to be ambiguous. This, on the other hand, is not ambiguous because the way we understand the for all, the way we understand is an element of, and the way we understand less than or equal to, which is defined up here, they are very, very specific. There's no room for ambiguation. Okay, Aidan said, quantified statements sound smarter too. Yep. Well, yeah, for people like me, I need every help to make myself sound smarter because I'm not. So there we go. All right. So the first question, okay, so getting back to this one, the first question is, does y have to be a part of x? In other words, is there anywhere in here that says y has to be an element of x? It doesn't say anything, right? So that's the first thing we kind of notice is, hey, so if x is a subset, okay, and we want to see if y is an upper bound of that subset of A, the initial set of A, there's nothing that says that the upper bound has to be a part of x itself. Okay, so that's kind of important. So now we define lowercase s as a variable. We define it to be the supremum of the set x. So this notation here is basically exactly the same, because if and only if, usually just means, is the same as the following. So now we have to look at this expression here and go like, oh man, what does that mean? Well, when you see something like this and the first reaction is, man, this is difficult to read, take a deep breath, okay? And then we just look at this step by step, okay? Because there's nothing is gonna help, okay? If we just look at this whole thing and just go like, oh, this is way too hard to understand, that is not gonna help. So what we need to do is to look at this step by step. So we look at the first one first, PSX, okay? P of SX. What does that mean? Well, according to what we saw earlier, it means, S, the lowercase s here, is an upper bound of x, which is a subset of A. Okay, that seems easy. Okay, that seems okay. Now we read the second part. This is conjunction. So there's a conjunction here, which means, just having lowercase s as the quote unquote upper bound of x is not enough. Okay, we need something else to be true as well. So what is this thing here? Let's take a look here. So this one says, for every s prime, okay, for all s prime, and then we have an implication inside the quantified statement. The implication says, if s prime is an upper bound of x, then s is less than or equal to s prime. So now somebody is going to ask, but what if it is not, right? What if s prime is not an upper bound of x? Then we are not concerned about that particular s prime, because when predicate p returns false, the implication is going to be true anyway. So it is not a concern. It is only a concern to us when s prime is an upper bound of x. Fine. What does that mean? Okay, what does this entire thing mean all the way from the beginning of the for all the way to the end here? Well, all that means is we want this lowercase s to be kind of the smallest of all the upper bounds of x. Let me say that one more time. It is the smallest, the least of all the upper bounds of x. That is what it means to be a supremum of a particular set x. It is the smallest or the least upper bound of x. Okay, the next sentence actually kind of explains that too. This basically means s is the minimum upper bound of x. Oh, okay. But isn't that really kind of the same thing as taking the maximum? Because isn't that really kind of the definition of maximum? Well, as it turns out, the answer is no. Okay, and that's why we have the next paragraph explaining why supremum is not the same thing as maximum. Okay, why is it not the same? Because supremum needs not be an element of x itself. Okay, so the supremum of x doesn't have to be an element of x, whereas the maximum needs to be an element of x. All right. All right. So now that we have explained all of this stuff here, okay. So Aiden just drew a picture. Right. So the supremum can be outside of the set X. It can be. It has to be in A, right? Because if it's not in A, then less than or equal to is not defined over, that particular element. So we know that the supremum has to be in A, but it doesn't have to be in the set X that we are talking about. And the reason why it may not we may not be able to find an upper bound within X itself has to do with A being only partially ordered. If A is totally ordered, then the supremum would have been the same as the maximum. But because A is only assumed to be partially ordered, that means we can find a supremum that may not be in X itself. So that's the kind of tricky part of being a partially ordered set instead of a totally ordered set. But what Aiden has drawn is a good way to look at it graphically, but because we are using the vertical location as an implication of the value of elements, and that the vertical displacement of something in the picture that Aiden had drawn is totally ordered. So that means it's still kind of difficult to explain what is a supremum. Yeah, so these are the kind of things that is a little bit abstract. Okay, so having said all of this stuff here, you guys are gonna hate me for doing this. Having said all of this, okay, when we are concerned about time complexity, and time complexity usually is a function that returns a real number, and real numbers, has a less than or equal to relation that is totally ordered. So that means, as far as we are concerned, for the purposes of time complexity, we can look at the supremum of x as the maximum of x. Okay, so within the narrow context of what we are using this stuff for, the relation less than or equal to is totally ordered, defined over the set, which is the set of all the real numbers. So we are actually okay of looking at supremum of x being the maximum of x. All right, so now we are going to define what is the infimum. I'm looking at the time. We still got about 25 minutes. So now we define what is the infimum. Infimum. There we go. So the infimum is the opposite. So for the most part, you can look at this as the minimum of x. Okay. So we have the maximum, we have the minimum within x. So now we want to talk about the concept of finding the limit of a sequence. Yep, all that calculus stuff is coming back now. Alright, so what we're going to do is we are first going to look at this kind of awful okay, first of all, we have to define what a sequence is. Okay, so a sequence of numbers is basically just a infinitely large tuple. So we have the first item of the sequence, the second item, the third item, and so on. Okay, and usually the values within the sequence, they usually are defined by some kind of a function, but not always. Okay, so in general, all we are really looking at here is, okay, so we have a sequence, an infinitely large sequence of numbers, and these numbers are typically real numbers, so they may not be integers, they may not be natural numbers, but they are usually just real numbers because we are talking about how much time it takes for something to be done. But we are usually going to say, the sequence is infinite, okay? Because the number of items in the sequence has to do with, or the position of an item in the sequence has to do with the size of the problem. So how big of an array are we trying to sort? Well, I mean, we don't want to put an upper bound to that thing. So that's why, the sequence is usually infinitely large. So now we want to look at this term here, and we want to find out what is the limit of this sequence. What does that mean when we are looking at the limit of a sequence? Well, that's exactly what this notation is trying to say. Okay, we are we are basically looking at I approaching infinity. What is the value of x of I when I approaches infinity? And that value is k. Okay, we're just using k as a placeholder to basically describe the limit of this particular sequence. All right, so we got a few people typing. I'm gonna wait a little bit here. Yeah, well, that's kind of why pre-calc is the prerequisite of this class. Because I think they touch on limits in pre-calc, and then in calculus they make use of the concepts already mentioned in pre-calc. So correct me if I'm wrong. Ooh, they never mentioned limit in pre-calc. Really? Well, that makes me wonder what they actually talk about in pre-calc. I can look it up, later. Huh. Okay. Well, interesting. All right. So, but it's okay. It's okay if they don't talk about limits in pre-calc because I'm going to talk about it. So what that means is k is a unique value that satisfies the requirement of this thing here. So now we look at this thing and go like, okay, that looks kind of difficult to understand, right? So remember what I said, when we see something like this, we break it up into smaller chunks and then we try to understand each smaller chunk, and then as we put the whole thing back together. Okay. So let's go ahead and start it. So basically this says for every epsilon that is a real number that is greater than 0, the following has to be true. Okay. So that means, all this part is saying is, okay, consider some epsilon that is not 0 as a real number. That's okay, I should not say not 0 because it's greater than 0. Okay, it's not less than 0, it is greater than 0. So that means we can now focus on this part here, knowing that epsilon is just a real number that is greater than 0. So this portion says, there exists m, which is a natural number. So m is an index into the sequence because the sequence starts with the index of 0, 1, 2, and so on. So when we think about the index z's of the values inside the sequence, the index itself is basically just a natural number. So this m here is basically saying, okay, we should be able to find a number within the sequence such that, such that what? Such that this thing is satisfied. Okay, so by the time we get to the for all j blah blah blah, all we need to know is epsilon is a real number that is greater than 0, m is a valid index into the sequence. Okay, then what? Then it says for all j that is greater than or equal to m as a natural number, k minus x of j in absolute value is less than epsilon. Whew, man, what does that mean? Okay, so first of all, what is j? What is the purpose of j here? J is being used as an index into the sequence. Okay, so when you look at where j appears, j is appearing here only as a subscript of x. So what that means is we can find a point within the sequence, whereas everything including that point and that point onward, all of those values are within epsilon of k. That's all it's saying. Choose any epsilon that is greater than 0. I should be able to find an m so that everything at index m and after are within epsilon away from k. That defines k. That defines the limit of the sequence, which is known as k in this case. So I'm going to pause here to make sure that we are okay with the understanding of what it means to take the limit of a sequence of numbers. I'm not seeing any traffic in the text channel. Oh, okay, here comes a little bit. Okay, all right, cool. I can use an example, by the way. Okay, so remember this is just an example, so don't the problem of using examples is some people kind of lock into the example and only remember the example, that's only supposed to illustrate a concept. So, but I will try anyway. But I think this is going to be helpful. Give me a chance. Give me a moment here to set up a spreadsheet, because the spreadsheet is particularly helpful in this case because I can look at the values, but I can also look at the graph. Okay, so we'll go ahead and use column A as our indexes. It starts with 0, and then the next index is going to be the previous one plus 1, and we can extend this all the way. It's supposed to be infinitely large, right? But I'm not, there's no way to represent something that is infinitely large using a finite state computer, which is basically all computers are finite state. All right, so now we basically look at x subscript of the index. So we need a way to define it. Okay, so I'm just going to define it as 1 minus 1 divided by, okay, obviously I cannot divide it by the index itself. I can say 1 plus the index itself, like so. All right. In other words, okay, so if I were to describe what is the sequence, so x of I is basically 1 minus 1 divided by 1 minus I. No, that doesn't sound right. That doesn't sound right at all. Okay, so let me see. What do I want to do? Plus. Okay, we want to plus 1 plus I. There we go. There we go. And I need to make sure my equation matches that. Yep, I used plus. Okay, but for whatever strange reason, I thought I used minus. But there we go. Okay, does everybody understand how each value is computed in column B? Because it's really just x of I. Okay, let me magnify this a little bit so we can see better. So each item here, okay, this is the index, which is I, and then this is the value of x of I. X of I is defined to be just 1 minus 1 divided by 1 plus I. So if I extend this equation here all the way down, yes, I could have just double click it. You can see how the values are getting closer and closer to 1. So are we okay so far with the way that I define this particular sequence? This is just the way I define this sequence for illustration purposes. I'm moving this over here because I have a purpose for column C. Are we still doing okay so far? Is everybody kind of still following me in this example? I'm just defining a very specific sequence so that I can illustrate and say, hey, what if I make this epsilon blah? Can I find an m that can satisfy that requirement? Everything at m, x of m, and past that point are going to be that close to the limit, which is 1 in this case. All right. So I'm going to give you the answer of k equals to 1. So k is the limit of the sequence. Okay, so k is the limit of I approaching infinity x of I. Okay, so that's the limit of the sequence, and that turns out to be 1. Okay. So now I want to find an epsilon. Okay, so column C is going to be, so I want to define epsilon here. So we want to define epsilon. That could be, okay, I probably spelled it correctly then. Okay, so we want to define an epsilon. Okay, we'll define epsilon to be 0.2. Okay, because epsilon is a real number that is greater than 0. So I'll just pick, 0.2 over here. Now I want to see if a particular value in the sequence is within 0.2 from k itself. So the way we can figure that out, okay, so the column here is to say, is xi within epsilon of k. Okay, so it's a Boolean thing. It's either yes, it is within that range, or it is not within that range, right? So now we evaluate the condition, and we ask if this value, if the limit, which is 1, minus the value, oh, okay, I need the absolute value too. So we look at the absolute value of k, which is 1, minus the the sequence, or the element in the sequence. If this is less than or equal to the epsilon that we have chosen here, which is f3, and I have to change this so that it refers to the row number in an absolute way, so that doesn't change. Okay, and that is basically what we're trying to figure out. Okay, f$3, and I don't actually need to use the if, so I'm going to get rid of the if here, because this is going to give me a Boolean value to begin with. All right. So at this point, you can see that x0 doesn't work for us, because it is exactly 1 away from k, which means it is not within 0.2 away from the limit. So the answer is false. So if I just double click this, and you can see how quickly I can say, oh, I have just found my m. Because when m equals to 4, then everything including x4 itself and everything thereafter, they are all within 0.2 away from the limit. All right? So this is a very specific example of using 1 as my limit and an epsilon as 0.2 here. Then somebody's going to say, but Tech, 0.2 is really kind of a large, I guess you can call it a margin of error, from the limit itself. So we'll make it smaller. So now we turn it into 0.1, and you can see how, hey, all we have to do is to move m, which is the index of the first item in the sequence, that is within epsilon away from the limit. It just move it down a little bit, right? On the other hand, if you make this even smaller, like 0.05, right? And we just move it down a little bit more, okay, starting at m equal to 19, everything including m19, m subscript 19, and everything after that, they're all within 0.05 away from the limit. So eventually, somebody's going to say, let's make this really small, like 0.01, okay? And we look at this sequence here and go like, haha, Tech, we have found something. We have found an epsilon where m does not exist. But hold on a second here, okay? Hold on a second here, because I can always, make more of this sequence visible, okay? Because we are only plotting up to item 67, because I didn't extend it all the way down, right? So we just have to kind of make it extend all the way down, and at some point we found our m. So we just have to go back and say, oh, okay, so when m equals to 99, okay, in other words, starting with x underscore 99, everything after that, including itself, are within this new epsilon that we have just randomly picked away from the limit. So the idea is I can make this epsilon smaller and smaller, and all that's going to do is to push the index of when we have the false to true transition further and further down. But it's always going to be possible. Okay, that is the whole point. It's always possible to find an m to meet the requirement as long as epsilon is greater than 0. So that means if I make this epsilon even smaller, okay, we'll make it 0.001, then what we have listed at this point in the sequence, none of this is going to meet that requirement, right? But if I extend this all the way down to, if I do my math correctly, down to I think 999 or 1000-ish, there's a certain offset to it, but the idea is it does exist, okay? I just have to extend the sequence, further down. Okay, at some point I released the mouse button and kind of messed up. Oh, right, there's my scroll bar. Okay, I'm just gonna look at the text channel here. Alright, so I don't see any questions, but am I getting the point across, or this is just making it more confusing? You can see that, I haven't found the index yet, because I think the index is going to be 999. I mean, that's just the math of it, right? But I do want to show you that it does exist, even though it is getting further and further away, but it does exist. So the idea is no matter how small I make that epsilon, I can eventually find the index that will make it true. That's the idea of the limit. All right, I'm going to pause here. Okay, we only got about 4 minutes left. Okay, so I'm not going to push any further. Okay, because I think just being able to understand the concept of the limit of a sequence is enough, basically for this portion of the class. But the idea of using a spreadsheet, oh, okay, there's one more thing I want to do before we stop today's lecture. Because when you just look at the number and the formula, in the spreadsheet, it can only give you a certain degree of understanding of what we're dealing with. On the other hand, if I plot it, okay, that should help us understand what we are dealing with. So we want to insert a chart. There we go. And we want to make this a XY chart. And lines only. Yep, sure. And we can make it straight. Doesn't really matter because we have so many points to begin with. So I can make it smooth, sure, and finish. There we go. All right, so when you look at a chart, that makes it kind of clear what we're dealing with here, because you can see how this line here is getting closer and closer to 1. So even without knowing, okay, without telling you what formula I use, for numbers in the sequence, just looking at the trend here, people would go like, oh, okay, so it is going to be closer and closer and closer to 1, because it graphically we can actually see how it is getting closer and closer to 1. But the idea is it never really gets to 1. Okay, in other words, even though we say the limit is 1, none of the numbers in the sequence is actually 1. It just gets closer and closer to 1. So that is the trick of taking the limit of something, is it is just getting closer and closer to something, and it will get infinitely close. Okay, I shouldn't say that because that's not technically or logically correct. So getting back to the definition here, okay, the definition is really important because all it says here is as long as epsilon is not 0, as long as it is greater than 0, it can be very, very, very small. And as long as it is still greater than 0, I'll be able to find this m. That's what it means when we find the limit of a sequence. All right, so, okay, so Li Yu has typed something here. Always approaching a number but never touching it. Well, touching is not required, okay? In certain sequences, maybe, it's in the sequence itself, okay? It is entirely possible, but it doesn't need to touch it. We just have to be able to find this m, no matter how small epsilon gets. As long as epsilon is greater than 0, we'll still be able to find an m where xm, xm plus 1, xm plus 2, they will all be within epsilon away from what we know as the limit. Yes, exactly. Except in the case in calculus, the way we use the limit is in conjunction with the definition of delta. So we are basically looking at the distance between 2 points, and we basically say, those 2 points get closer and closer and closer and closer, and we're trying to find the slope between those 2 points, and that's the way we use limits in calculus. So in that sense, okay, in the case of calculus, it is not discrete because we are not trying to find, it's not a sequence that we are talking about. But in this class, we're talking about a sequence where we basically just have discrete numbers along the sequence, and we are basically just saying, okay, as we move along down the sequence, given a particular epsilon that is greater than 0, eventually we'll find a value in the sequence that is within epsilon away from the limit. And guess what? Everything after that, all the values after that particular item in the sequence, will also meet the requirement of being epsilon away or within epsilon away from the limit. So they're related. Understanding how we use limit in calculus obviously is going to help in this case as well, because they are really kind of a very similar way of using that concept. Except in calculus it's continuous. In this class it is discrete. It is not continuous. All right, cool. So we are running out of time today. So I'm going to stop here, okay? But I want you guys to read ahead of me because there are sequences where the limit does not exist. Okay, and you might think, oh, maybe we have a sequence where the values just keep going up and up and up, and therefore there's no limit. Well, there are those too. Okay, but we can also define something as simple as this, where x of I is -1, the whole thing to the power of I. I should put parentheses around the -1 because that really is kind of important. But -1, the whole thing to the power of I, is a very simple sequence, right? Because it starts with 1, then -1, then 1, then -1, then 1, then -1. But that sequence has no limits. Okay, so when we encounter sequences like that where it just kind of oscillates, but it never really settles down, between the oscillation, what are we going to do? So that is what we'll be talking about next Monday. So we got quite a few concepts to kind of understand about all the stuff that we have talked about so far before next Monday. So you guys got some, reading and reviewing to do, before next Monday. Yep, it is oscillating, but without attenuating the amplitude. Because you can also have oscillation where the level or the amplitude of the oscillation keeps going smaller and smaller. So in those cases, you still have a limit, even though it goes up and down, up and down, up and down, because the amplitude is going to get smaller and smaller and smaller. You'll still be able to find that index m given a particular epsilon. But in the case of -1, the whole thing to the power of I, the amplitude of the oscillation does not change. it is always going to be 1, -1, 1, -1, 1, -1. So this claim here, there's no way we can find an m to satisfy all the requirements given that epsilon only has to be greater than 0. So that's why this particular sequence has no limits. Alrighty, so I'm gonna stop the lecture at this point, stop the streaming. If this is kind of abstract to you, then you just have to spend some time to dissect these types of statements and do it step by step. Okay, just really do it step by step. One layer at a time. And so by the time you get to the innermost portion here, you understand the context of what each one of these variables is representing. What is epsilon representing? Oh, it's just representing a certain range around the limit. What is m representing? M is representing an index. It is the starting point in the sequence where everything from that point and on will be within epsilon away from the limit. What is j? Well, j is really just saying, okay, anything that is after or equal to m in the sequence has to meet this requirement. So you just have to kind of basically peel, like peeling an onion with all the tiers too. Just peel away these statements, one layer at a time. So that's all I can recommend. All right, so I'll see you guys next Monday. Have a nice weekend. And obviously, I will still be available during the office hours if you need to ask questions. I just put the exam 1 scores out. Those should be sent to your apps.losrios.edu email already, like more than an hour ago, before the lecture. So you might want to check your email, Anita. If you don't get it, let me know, because that means something is not right with my script. All right, so I'm gonna stop streaming and have a nice weekend.